Hi, I'm Norman Wildberger, and today we're going to introduce the omega triangle of a given triangle. This is part of chromogeometry, our new threefold symmetry that brings together usual Euclidean blue geometry with two relativistic geometries called red and green. Our setting is a triangle in the Cartesian plane, the triangle A1, A2, A3 here in black. It's in the Cartesian plane, meaning that we have specified coordinate axes which are pinned down. And it's the position of this triangle with respect to these coordinate axes which is crucial in setting up this chromogeometry. The first thing to note is the three midpoints of the sides and the centroid, which is the intersection of the three medians of the triangle. A median is just a line through a vertex and the midpoint of the opposite side. So they are the three medians and they intersect at the centroid. And it's an important basic observation that that centroid splits each median into the ratio of 2 to 1. It's a basic fact. And we're going to see how that relates to Euler lines in a second. Now, the three Euler lines, the blue, the red, and green, are defined by passing through the corresponding orthocenter and the circumcenter. And they turn out all to pass through the centroid as well. So the orthocenter, I remind you, is the intersection of the altitudes of the triangle, the lines which are perpendicular to the opposite sides. The circumcenter is the intersection of the perpendicular bisectors of the triangle, and those are the lines that are emanating from the midpoints and perpendicular to the sides. Because it's on each of the perpendicular bisectors, this circumcenter is equidistant or equiquadrant to each of the 3 points of the triangle, and so there's a unique circle going through the 3 points which has its center here. Now those statements hold equally well for the red and the green geometries. So here's a red orthocenter, a red circumcenter. Again, the intersection of the 3 red altitudes, intersection of the 3 red perpendicular bisectors. And there's a green orthocenter and a green circumcenter. Again, intersection of the 3 green altitudes, intersection of the 3 green perpendicular bisectors. And now we're going to introduce the omega triangle, which is just the triangle formed by the 3 colored orthocenters. O sub B, O sub R, O sub G. So this is going to be called the omega triangle of the original triangle A1, A2, A3. And this triangle here organizes all the other data in a very pleasant and simple way that it's easy to remember. Okay. Because of this crucial fact that the circumcenters are the midpoints of this triangle. So this one here is the midpoint of OGOB. This one here, the blue one, is the midpoint of OG and OR, and this one here is the midpoint of that. That has some immediate consequences. So that means that this triangle here, together with these 3 lines, what we're seeing there is an example, just as we saw starting with, of a triangle and its 3 medians. The Euler lines are just the medians of the omega triangle, because they pass through a vertex and the midpoint of a side. That has a lot of consequences, non-obvious consequences. For example, a line joining 2 midpoints is necessarily parallel to the opposite side. So the line joining the blue and the red circumcenters has to be parallel to the line joining the blue and the red orthocenters. And similarly, that line is parallel to that one, and that line is parallel to that one. But moreover, the ratio of this vector to this vector is in the ratio 1 to 2, because this triangle here is similar to this triangle in the ratio of 1 to 2. So we can also say that this quadrant is 1/4 the quadrants of this one in each of the 3 geometries. And similarly for the other ones, this is 1/4 of this one, and this one is 1/4 of this one in quadrants. Now there's some additional 3 points which are also interesting, and these are the 9-point centers. The 9-point centers is what we get when we do the circumcenter construction to the triangle of midpoints of the original triangle. So what we're doing is we're looking for the center of the circle that passes through the 3 midpoints. That's called the 9-point center. So for the blue geometry, that's that point right there. That's the center of the circle that passes through these three midpoints. And it's obtained by reflecting the circumcenter of the big triangle through the centroid in the ratio of 2 to 1. This is this Euler dilation. So the same dilation that takes a vertex and reflects it in here to get the midpoint, that same dilation takes this point here and gives us the 9-point center. So that's also in the ratio of 2 to 1. Since this vector to this vector is in the ratio of 2 to 1, and this to this is in the ratio of 2 to 1, it follows that this 9-point center is midpoint between OB and CB. That's telling us that this 9-point center actually lies on this line here, because this is the line that's halfway between this point and this vertex in the omega triangle. So the 9-point centers are simply the intersections of the medians of the omega triangle with the lines joining the midpoints of the omega triangle. And now we see that this 2 to 1 aspect in the Euler lines that Euler discovered can be seen as a direct consequence of the geometry of the fact that our omega triangle has these 3 points as its midpoints. So therefore, this to this is going to be in the ratio of 2 to 1. So it's well worth thinking about that and sort of pondering it. Next time we're going to have a closer look at the significance of these 3 9-point centers. And we're going to talk about what the corresponding circles look like. It's easy enough for the blue one, just a regular circle, but for the green and the red situations, we're talking about rectangular hyperbolas. And they have also very pleasant properties, exactly in parallel with the properties of the 9-point circle that we've talked about earlier in this series in our triangle geometry videos. So please have a look at those to remind you, and next time we'll talk about the 9-point circles with respect to chromogeometry. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.